Hello. Hello, everyone. Okay, so let's start. Let's start, not wait for anyone to join. Can you hear me? Just being a bit slow. Wonder. That's what you get if you don't restart the computer for a very long time. Okay, you can hear me. That's brilliant. And okay, you should be able to see my screen now. Can you see my screen? Just let me know. And we get more participants. That's lovely. Lovely, great. Right, so today is Pulleys. Today's topic is Pulleys. I hope you have seen the assignment. The assignment has been published yesterday for year 10 and today for year 11. This is the final assignment for year 11. So well done if you've made it this far. So that's great. And it's assignment number 6 out of 10 for year 10. And we start with constraints. In physics, sometimes we have constraints. And so what is a constraint? Well, it's very simple. It's reasonably simple. If you have two objects which are tied together, let's say you have a toy car and another toy car, and if they're tied together with the string, that is the constraint. And that means, like, as long as the rope is taut, yes, as long as the rope is taut. If this car is moving at 3 meters a second, and this car is moving at 3 meters a second. If this car moves 20 meters, then this car moves 20 meters. And also, importantly, if this car is moving with acceleration, let's say 2 meters per second squared, this means that this also meters per second squared. Constraint is when knowing A, V, or S for one object, we immediately know A, V, or S for another. No. It's not always that simple, right? The constraint, like for example, in your bones, the parts, the joints in your bones allow your hand to move in one direction only. It doesn't allow, if I fix this, I can't move my my shoulder left to right. Okay, my not shoulder, but the other, my hand. I can only move it if I twist here, because this is the twisting happens here if I turn my hand. So the fact that my elbow doesn't allow my hand, my palm move in this direction, that's a constraint, right? So all sorts of constraints in mechanics that we have. Right. So yeah, that's the idea of constraints. Why are we talking about it? Well, let's say you have a pulley and there's a rope. So, and you have two masses, M1 and M2. M2. If you know for a fact that this mass is accelerating up at acceleration equals 3 meters per second squared, then you know for a fact that this one is also moving with acceleration 3 meters per second squared. Okay. Now, technically, that would be minus, but you don't need to worry too much about it, as long as you get the arrow correctly. Now, okay, does that make sense? Any questions? Now we have two types of pulleys. We have a stationary pulley. A stationary pulley is attached to a stationary object. So for example, the ceiling. Attached to the ceiling, that is a stationary pulley. Stationary pulley. And we have a moving pulley, which is attached to a moving object. So for example, it's a box and there's a ceiling and there's a rope like this. And if we apply a force here, this pulley, this mass is moving. So this is a moving pulley, movable pulley. Is that acceleration not positive considering gravity? It's a matter of choice. Before you do any question, you decide. And my decision was up is positive. That's my choice. It doesn't matter how I choose, as long as I've chosen the direction at the beginning, and then I said this is +3, this is -3. So gravity in this case would be minus 10 newtons per second, well, meters per second squared. Meters per second squared. Right? Does that make sense? It's so when you do a question, you make this choice, and then you stick to that choice. Yeah, you can't switch halfway through. But as long as you are consistent, you'll have no problem. And then you know if the answer is positive, that means it's up. If the answer is negative, it means down. Stationary pulley, well, it's simple. The object is moving. So we apply a force. We apply a force F. The object is moving, but the pulley is stationary. No. I mean, if you're doing, that's a very good question. Okay, let me just pause for that. So, positive versus negative acceleration. So imagine I'm falling from a tree. Something I have never done, but I'm very surprised with the amount of trees I've climbed when I was a child. I've never fallen off. So imagine I'm falling from a tree. So the tree is, let's say, 4 meters. Okay, that's cruel, but there's something soft in here. So 4 meters, and I start with 0 velocity. So I can do a suvat. Now I decide that up is positive. I keep this in mind, up is positive. So my displacement, because I'm falling down, my displacement is going to be -4. Initial velocity 0, final velocity we don't know. Acceleration is -10 because acceleration is down, and time is question mark. Or you can say, I don't want up to be positive. I want down is positive. And then I do s equals 4 because I'm moving down. Initial velocity 0, final velocity we don't know. Acceleration is 10 and t. But then any formula you use, you will see that the two minuses cancel out. So it doesn't matter where you use 4 and 10 or -4 and -10. So if they eventually will cancel out, if you, let's say, you're doing s equals ut plus 1/2 at squared, because this is 0, so this is going to be 4 equals 1/2 multiplied by 10 multiplied by t squared, or you have -4 equals 1/2 times -10 times t squared. You see what's happening? You just make a decision. It doesn't matter what you choose. As long as you stick to that decision, then you get the same answer. Okay? I usually say the y draw the y axis, and then choose a direction. So now the y-axis is up. So up is positive. That's it. Lovely. So the question was, why does a movable pulley increase the force? A movable pulley is a force multiplier, and we need to work out why it is a force multiplier. So imagine I have a movable pulley. So I have a stationary rope, and then I have a pulley. And another rope. And this end of the rope is fixed to the ceiling. Now I apply a force here, and this allows me to lift a force here. Right. So you can see that if you move slightly up, if you move, I don't know, if you move 10 centimeters up, you will see that this moves up, and you will see that if you moved up by 10 centimeters, if this end moves up by 10 centimeters, this end only moves 5 centimeters. You see that? Now, you're moving a smaller distance because this point is stationary. So this is the pivot. And if this is the pivot, let's draw it like this. Pivot. And this distance. Let's say this is the radius of the pulley. So this length is 2r. So if I apply a force here, let's say it's a 10 Newton force, 10 Newton force, then the moment is force times distance, right? Force times distance from the pivot. So it's 10 times 2r. Now, what's the other force here? What's the force here? F, which is we're looking for. Because the distance is only r, but the moment has to be the same. Moment is F multiplied by r. Because the moment of both forces has to be the same, then we have F times r equals 10 times 2r. So F is equal to R cancels. F is 20 newtons. So the force here is 20 newtons, whereas the force here is 10 newtons. So you win, you double the movable pulley allows you to double your force. Movable pulley. Movable pulley doubles the force, but halves the distance traveled. Does that make sense? Right? This is what we call a force multiplier. It's like, well, like a lever. You can see that this part of the pulley acts as a lever. You have a force here, and you have a force here. So they because this force is applied further away from the pivot, it means this is a bigger force. So if this is 10 newtons, then this is 20 newtons. It's quite handy, right? Okay, no questions here? Why is the distance between the center of the circle and the center of the second boot 5 centimeters? Well, because look, this end of the rope is fixed to the wall on one side, and it's attached to the here to the pulley. So if you move, like, so this point is stationary, does not move. Stationary point. Because the length of the rope cannot change. It's here. So if this end moves up by 10 centimeters, then this is stationary. Then this has to move 5 centimeters by just the principle of geometry. It's like the middle line of the triangle. They're just like this. If the middle point moves by, if this end by 10 centimeters, that moves by 5 centimeters. It's not exactly the well, yeah, it is. Okay, technically, I mean, this rope does become shorter. It has to. It has because the pulley will roll above, but at any given moment, stationary at any given moment, Of course, we climb up the rope anyways, but you can work this out. Hence, if you have a movable pulley, let's say you have two pulleys. Okay, let's do it properly. Pulley 1, pulley 2, and some. So let's say this is M1, mass M1, and this is mass M2. Make it pretty. So M1 is attached to a movable pulley, and M2 is attached to a stationary pulley. Now, if M1 moves 10 centimeters down, how much does M2 move up? Five centimeters. Yeah, exactly. Moves 5 centimeters up. Very good. But when you realize that displacement x is the displacement, so x, yeah, velocity is the derivative of the displacement, and acceleration is the second derivative, is the derivative of the velocity, dv dt, which is d squared x dt squared. If you replace x with half x, the acceleration will also be half. So if the acceleration of this object, if this acceleration a2, and this is acceleration a1, then we can say that a2 is double a1. That's a very important, that's another, that's also a constraint. Constraint. Does that make sense? But I prefer, personally, that if I have this, I would say let this acceleration be a, then this acceleration is 2a without any indices. All right, so I make one of the accelerations, I say, so this is going to be a, and this is going to be 2a. Or you can say that this is a and this is a over 2. But I mean, if you can avoid fractions, avoid them by all means. And this is what we're going to use a lot today. So hopefully I've done the necessary stuff. So let's see if we can do these questions. Right, so we have three masses connected by ropes. Okay, so what we need to do is find the acceleration and the tension in each string. So the first thing we notice that, of course, these two masses are moving to the right. That's to the right and down. And because they're connected to the rope, what can we say about their accelerations? Very equal. Very good. So if this acceleration is a, then this acceleration is also a, and this acceleration is also a. Right. Now we draw each mass separately. and just draw the forces acting on each mass. So for the first mass, there is the tension pushing to the right, pulling to the right. So there's the tension T1. It's the first rope, T1. And there's friction. And there's friction here. And because it is moving, we already know that the friction is equal to mu R. But R is mg, isn't it? Yes, the upward force. Because if you look, this is R, reaction force, and this is mg. R has to equal to mg. Right? So the friction force is mu 1 m1 g. Does everyone understand how I got this value? Mu 1 m1 g. I'm happy to explain if you're not sure. Friction force is mu R, mu times the reaction force, and the reaction force is mg, so it's mu mg. I can ignore the vertical forces because I mean I consider the vertical forces. So now I write Newton because it's accelerating to the right. I can write Newton's second law. Newton's second law says that m1 m1a is equal to the resultant force. And the resultant force in this case is T1 minus mu 1 m1g. So overall, m1a equals T1 minus mu 1 m1g. That's the first equation. Now we draw the second mass. It's also accelerating with acceleration a. And there's T2, the tension in this rope, T2. There's T1 pulling left, T1. And there's another friction force. The friction force is mu2 m2g. So I can write down Newton's second law. m2a is equal to T2 minus T1 minus mu2 m2g. That's the second equation. Now for the third block, block, we only need to consider the vertical forces. So there's T2, there's the tension in the rope, T2, and there's M2G pulling down. Oh, mg pulling down. So mass times acceleration is equal to mg minus T2. That's the third equation. Now, how many unknowns do we have? We have A. We have three equations. Unknowns. A is unknown, T1 is unknown, and T2 is unknown. So we have three equations, three unknowns. Voila. All we need to do is solve the simultaneous equation. Now, it may seem like daunting, but it's actually so not difficult. Because all you need to do is add all the three equations. So let's label them. This is equation 1, this is equation 2, this is equation 3. So I'm adding 1 plus 2 plus 3. I get m1a plus m2a plus ma equals T1 minus mu1 m1g plus T2 minus T1 minus mu2 m2g plus mg minus T2 And look at that. Look at this beautiful situation. We take A as a common factor, M1 plus M2 plus M equals mg minus mu1 m1g minus mu2 m2g. It kind of makes sense because you have an object of total mass m1 plus m2 plus m, which is accelerating with acceleration a, and this acceleration is caused by three forces: mg pulling down and two friction forces that are preventing you from accelerating. Right? So this is an object of mass m1 plus m2 plus m, accelerating with acceleration m, repeating myself, which is, in this acceleration is caused by three forces: one pulling down and two forces preventing you from accelerating, which is the friction forces, which makes, so what you can do is you can say, well, look at that. We have one force pulling down. This is mg. And there's two friction forces here, F friction and F friction. That's it. And then you have total MA equals the resultant force. So mass, which is M plus M1 plus M2 times A times acceleration is equal to mg minus F friction 1 minus F friction 2. And that's exactly what we got here. That's what we arrived at. And okay, so all I need to do is find A. So A is, and then I'll be a bit. Divided by M1 plus M2 plus M. And that's the answer. Now, if you want to find T1 and T2, then you just substitute into one of the equations, substitute that into one, substitute that into equation 1, and then you get T1 is equal to M1A plus mu1 M1G. And it just comes down to calculating it. And then you substitute that into equation 3, and you get T2 is equal to mg minus ma. And that's it. I don't want to calculate that. How well do you understand this problem, like overall? On a scale of 0 to 10, please. The remaining questions are going to be easier. Okay, very good. So problem 3, we have two masses over a pulley, and there's a hole in mass M2, and it can slide. Yeah, sorry.
He's awake now.
What's that? Mark, do you have a question?
Just woke up.
Okay. Just give me a minute, please, okay? I'll come back. Right, sorry. Yeah, had a crying baby incident. So we have a hole in the second mass, and the second mass slides up and down. So the shaft, but can you call it? I don't know. It can slide through, and there's a friction force here. Find acceleration and the tension in the string. So we just do the same thing. We draw the first mass, and certainly you can see that it is heavier. So this one is going to move down. Let's say this is moving down with acceleration a. Because there's a constraint, this one will move up with the same acceleration a. So m1 is moving down, and this acceleration is caused by two forces. It is caused by the gravity, mg, m1g, and tension, T. So Newton's second law tells us that mass acceleration, m1 acceleration, is the resultant force. And the resultant force is the forces that help you move forward minus the forces that prevent you from moving forward. So it's the m1g minus T. That's Newton's second law. This is incredibly important. If you're not confident with this, please talk to your tutor. Go through a lot of examples until you get it. Because once you get it, it's an open road. Now for the second mass is moving up with acceleration a. And this acceleration is caused by three forces. So there's the tension, there's the gravitational force, m2g, and there's a friction force, which is down because it's preventing you from moving fast. So that's F friction. So we can write this down. We can say that m2 mass acceleration is equal to the forces that help you move forward, so T, minus the forces that prevent you from moving forward, so m2g minus F. This is the philosophy of Newton's second law. And then all you need to do is just figure out how many unknowns. Two, A and T is unknowns. Unknowns. A and T. And yeah, all you need to do is just, oh, you can add the two. So 1 and 2. You do 1 plus 2. This is this 1 plus 2. Let me just finish this one. So it's going to be m1a plus m2a equals T cancels. So it's going to be m1g minus m2g minus F friction. So acceleration is equal to m1g minus m2g minus F friction divided by m1 plus m2, and that is half a kilogram, so 0.5 times 10 minus 0.1 times 10 minus 3 newtons friction divided by 0.5 plus 0.1. So 5 minus 1, 5 minus 4 is 1 divided by 0.6. So that's something. 1 divided by 0.6 is 1.67. 1.67 meters per second squared. And tension we can work out from the first equation, is the easiest one. From first equation, tension is m1g minus m1a. So it is m1g, which is 0.5 times 10 minus 0.5 times 1.67, and that gives us 0.5 times 10 minus 0 times ounce. So it's 4.17 newtons. So this is the acceleration, this is the tension. Right. I have a question. If M2 was heavier than M1, would it pull down M1 more? It was arranged vertically or horizontally. Well, if M1 was arranged horizontally on a horizontal table, the gravitational force of M1 wouldn't matter. The gravitational force would be compensated by the normal reaction force, and so the tension would be the only force acting on M1. So there is friction because it's sliding on along a shaft, right? Because the stick is in the shaft, so there's friction. If it was the other way around, it's just there wouldn't be much difference. Just the size would be different. Okay, and the acceleration would be m2g minus ma minus f friction. So yeah, I hope that answers the question. I'm not 100% sure what you were asking, but I hope that Ikshita, does that answer your question? Does that help? I mean, what I said. Okay, I hope so. If M1 was on a table, then M1G would not be pulling on the rope. M1G would be pulling down against the table, which there would be no more reaction. So the only force would be the tension. Number 4. Assuming no friction, just a second. Can we skip number 4 and just go to number 5? So number 5 is this exactly the same as one of the questions from the assignment. Okay, so this is my my gift to you. I'll do a different value. So find the force. So let's say this is m equals 60 kilograms. Find the force needed to move the mass with acceleration 3 meters per second squared. Okay. So what force is needed? Well, force, if you're pulling on the rope, the tension on the rope has to be F. So if you draw the mass M, there's the tension force up, there's mg down, and the mass is accelerating up. So we write down Newton's second law. Mass acceleration equals the resultant force. So mass times acceleration is equal to the forces that are pulling you up minus the forces that are pulling you down. So mg. And then you just rearrange to find t. Or t because F is t. So t is ma plus mg. And in this case, you can ma plus g. So m is 60 multiplied by 3 plus 10. 2 plus 10 is equal to 60 times 13. 60 times 13. 780 newtons. Mass up. Now, let's do the same problem. But force needed to move the mass down with acceleration. Now, the mass is now moving down with acceleration, and there's tension force and there's mg force. Now, in this case, to move down. Okay. Now, mass acceleration is equal to the forces that push you forward, so mg, minus the forces that pull you backwards, so minus t. So in this case, t is equal to mg minus ma, which is m, open bracket, g minus a. So it's 60 multiplied by 10 minus 3, which is 60 times 7, which is 420 newtons. So if you want to lower it at acceleration 3, then the force is going to be 420, 780. Now notice that I haven't used acceleration equals minus 3. I could, but what I'm doing is I'm saying, well, acceleration is down and it's positive. It's positive and it's down. And when I write ma equals the forces, because at this point, I'm saying the forces that help you move minus the forces that prevent you from moving. That works. Because if I could say up is positive, and then sorry, it's the same thing as saying down is positive, right? Because I'm moving down and I'm saying down is positive. That's why I'm doing mg minus t and not t minus mg. At all times, I want a to be positive. So I always try to choose a direction such that a is positive. Okay. And you'll see that happening a lot today. Let's do this one. So yeah, sorry, the answer, okay, I got the answer here. So the force needed, find the force needed to move with acceleration, move up with acceleration 3 and move down with acceleration 3. Now let's talk about this one. Find acceleration A1, A2, and find the tension in each string. Right. So interestingly, let's say, for instance, that this is 200 grams and this is 300 grams. Which way will they move? So the 200-gram mass, will it move up or down? The 200-gram will move down, but the 300-gram is heavier, isn't it? Ah, very good. So Luke has very observantly said that the 200-gram mass will move down because it's a force multiplier, which is indeed true. But let's say we are not as observant as Luke, okay? And we went with our first guess, and it is perfectly fine. We say that this one is moving up and this one is moving down. But we know the constraints. We know that if the acceleration of this one is, the acceleration of this mass is, let's say, a, then the acceleration of this mass is going to be a over 2 because of the constraint, right? Because if this will accelerate twice less than this one because it is a movable body. And now I can write down the forces, and you can see that there's a tension force here. There's M1G force here. There's tension force here, tension. There's a tension force here. There's two tensions and an M2G here. So drawing the first mass, M1. So there is M1G and there's the tension and it's accelerating up with acceleration A. So I write down M1A is equal to the forces pulling you up, T, minus the forces preventing you from moving with that acceleration which you have chosen, minus M1G. That's the first equation. Now you draw the second mass. Draw the second mass, and there's M2G, M2G. And there are two tension forces, T and T. And it's moving down with acceleration A over 2. So writing Newton's second law, M2A over 2, mass times acceleration, is equal to M2G minus T minus T, minus 2T. Okay. So what I want to do now is I want to multiply this equation by 2. This gives us 2m1a equals 2t minus 2m1g. And this is so 1/2 m2a equals m2g minus 2t. Why I multiply this by 2? Because I want to cancel 2t. So I add the two equations. So I add 1 plus 2. And that makes us 2m1a plus 1/2 m2a equals m2g minus 2m1g. So acceleration, open bracket, 2m1 plus m2 over 2 equals m2g minus 2m1g. So the acceleration is going to be m2g minus 2m1g divided by 2m1 minus m2 over 2. And another cool thing about this one is that because I have mass on top and mass on bottom, I can use grams instead of kilograms because they won't cancel out. So, and you can take G out. You can take G and say it's multiplied by G. So G, so M2, which is 300, minus 200 times 200, so that's 400, divided by 2 times M1, so that's 400, minus M2 over 2 minus 150, and that gives us minus 100 divided by 250 G, which is minus 100 divided by 254, 0.4, 10. Yeah, it must be 0.4. It's minus 0.4 G, which is minus 4 meters per second squared. So I've got a negative answer, but that's not a big deal. That means my initial guess was incorrect. I guessed the direction incorrectly. So the minus means I guessed the direction incorrectly. So in fact, so M1 moving down, not up. And yeah. So you see what I did here? Do you understand do you understand what I did? I initially guessed acceleration, that acceleration is of M1 is up and the acceleration of M2 is down. But I got a negative answer. That means my guess was incorrect. So all I need is just to, well, say that they're the opposite direction, not up. Therefore, so acceleration A1, acceleration of the first mass is 4 meters per second squared down. Acceleration 2 is half that, so it's 2 meters per second squared up. And tension, well, we can find tension just from any, it's M1A plus M1G, which gives us M1, which is 0.2 multiplied by, you need to be careful because here you cannot use grams, otherwise you get into trouble, and that's acceleration is 4 multiplied plus 10. 0.2 times 14 is 2.8 newtons. That's it. That's the problem. Once again, I've shown you this before. Have you noticed that everything up to here is physics and everything else is maths? Maths. Well, maybe except this bit. Maybe except this bit, which is also a bit of physics. The understanding of it, but all you need, like physics, in my view, is the physics is applied maths. I wouldn't agree with this statement. This is what a maths teacher would say. Because a typical maths teacher wouldn't know physics. Sorry. A physics teacher would would never say physics is applied maths just because they know physics well. So yeah, mechanics is applied maths, perhaps. That's about it, but not the whole of physics, certainly not. So yeah. Right, so what would I show you? Sorry, I don't. There's a question. Sorry, I don't understand why the minus answer means the answer was wrong. Not the answer. The numerical answer is correct. It's just I said I don't know which way M1 is moving, up or down. I'm gonna guess that it is moving up. And when I did the calculations, I found that the answer is negative. And that means that it is not moving up. It is moving down. Does that make sense? I need a yes or a no. Okay, so when you guess the direction acceleration, you assume the direction is positive. I assume that it is moving up, yes. So when you guess the direction acceleration, you assume the direction is positive. I assume it's moving up with acceleration A. And then I find that A is negative. That means it's moving down, not up. That's the idea. So if you don't know the direction, it's okay to guess the direction. And if you get a negative result, that simply means that you've guessed the direction incorrect. I've got 3 questions. I'll have time. I'll probably have time to go through one. So I have 2 very basic questions and one the harder questions. Okay, if you want to do the harder questions, type harder. If you want to do the more basic question, write basic. What's your choice? Let's have a vote. Okay, I like the spirit. So this problem combines the first topic. It's a combination of the first topic, which was hydrostatics, and Newton's second law. 2 identical balls are placed as in the diagram. The terminal velocity of a ball falling through the liquid is V0. Water resistance is proportional to speed. Find acceleration and find the terminal velocity. Terminal velocity of the system and the tension shown in the rope. Okay. Interesting. So we need to identify the forces acting on the masses. So for the first mass, it's very simple. It's going to be mg and tension. Which way do you think it will be moving, up or down? The balls are identical. Why up? Sorry, there's a floor here, yeah? Is this which is denser than air? But the water is standing on the table. So, well, there's an upthrust force. There's a buoyancy force. The water is pushing the ball up. So there will be tension, of course, tension in the rope. There's mg, but there's also the upthrust force. And there's another force. So because it's moving up, because it will be this mass will be moving up, there will be a water resistance force. So let's look at the whole. Let's look at it in more detail. And of course, this one is moving down with acceleration a, and this one is moving up with acceleration a. The accelerations are the same because they're connected by a rope. So first ball, we have mg down, and we have tension, and it's moving down with acceleration a. So we have ma is equal to mg minus t. So this is standard stuff. Second ball, the story is a bit more complicated. We have the ball is moving up with acceleration a. Sometimes you use two arrows for acceleration, just not to confuse it with a force, but there's nothing else to it. So there's the tension in the rope. Then there's mg, which is down. There is the water resistance F, water resistance, and there's the upthrust force, upthrust. So mass acceleration of this ball is going to be the forces that help you move forward, so T plus U, minus the forces that prevent you from moving forward. So this is force of the water minus mg. And then it says water resistance is proportional to speed. Water resistance is proportional to speed. Well, that means that the force of the water resistance is K multiplied by V, by velocity. Right? So F equals KV. Does that make sense? Water resistance is proportional to speed. It's K times V, where K is the coefficient of proportionality. Oh, where? Brackets. Around the T plus U. No, it doesn't matter. Force is pushing you up, minus force is pulling you down. T plus U. Now, what does this mean? What does this mean in terms of acceleration? If it's a terminal velocity, do you know the acceleration? If it's a terminal velocity. Zero, yes. Of course, because if you let go of the system, it will accelerate until it reaches terminal velocity, because as it speeds up, the water resistance increases. All right. So acceleration is zero as it is terminal velocity. Terminal acceleration is zero. So we have 0 equals mg minus t. That's the first equation. And here we see 0 equals t plus u minus kv minus mg. But from here, we have t must be equal to mg, because if it's moving at constant speed, the tension must be equal to mg. Right? And that makes perfect sense. If there's no acceleration, t has to be equal to mg. And therefore, we have 0 equals mg plus u minus kv minus mg. Mg cancels. And we have upthrust is equal to kv, the velocity. So upthrust, as you already know, upthrust is the density of the liquid multiplied by gravitational times the volume of the ball. The volume of the ball. And that's equal to kv. So the velocity is the density of the liquid multiplied by gravity multiplied by the volume of the ball, which we do not know, divided by k. So we don't know the volume of the ball, we don't know k. So what are we going to do with this? Well, we haven't considered what happens when we haven't used V0 yet, right? The terminal velocity of the ball through the liquid is V0. So what does that mean? Well, that means if we take the same liquid and the same ball and we release it, it will fall through the liquid at terminal velocity. So the forces release a single ball, release a single ball. It falls through at terminal velocity, so it has mg. Now it has upthrust. Upthrust is equal to density of the liquid multiplied by g multiplied by the volume of the ball. And then there is k v0, because it's falling at v0. And acceleration is 0. So mass acceleration is equal to mg minus k v0 minus rho l g v. Because this is 0, we can say that mg is equal to k v0 minus rho l g times the volume. But then remember that the mass is the density of the ball times the volume of the ball. So density GV equals KV0 minus rho L GV. Now take everything to the left. So rho liquid plus rho GV is equal to KV0. And from here, we can express K. K is equal to rho liquid plus rho G volume divided by V0, where V0 is the terminal velocity of a single ball. And now we substitute that into here. It's the rho of the liquid, G, times the volume, which we don't know yet, divided by K, which is rho liquid plus rho GV V0. So G and V cancel, and we're left with rho liquid V0. Actually, rho liquid divided by rho liquid plus rho of the ball times V0. And that is the answer. That is the speed. So if you know the densities and you know how fast a ball falls through the liquid, you can work out how fast it will rise through the liquid in this situation. Oh, plus, where would it be plus? Sorry. Yes, you are correct. I'm sorry. Of course, so this is going to be plus. This is plus. So this would be minus rho liquid. Minus rho liquid. That makes more sense. Should have done a sanity check here. Minus rho liquid. Minus rho liquid. So the answer V equals rho liquid divided by rho minus rho liquid times V0. Okay, sanity check. Sanity check. Let's do sanity check. Well, we can assume that the density of the liquid is 0. If the density of the liquid is 0, that means it's the same as air. Then velocity would be 0 divided by rho multiplied by V0, which is 0. The terminal velocity would be 0. That makes perfect sense. If there was no liquid here, the whole system would be stationary. Okay? It makes perfect sense. Velocity would be 0. System would be stationary. System would be stationary. Be stationary. Right. So we've passed the sanity check. And of course, if density of the it doesn't make any sense. Okay, yeah, that's a sanity check. What I said if. What if? If let's say so if the liquid is air. Okay, the density of air is not 0, but it's very close to 0. If you're talking about a metal ball, for example, and yeah, so if there's no liquid, basically, that's what I'm saying. If there's no liquid, then it would be stationary. It would be stationary if there was no liquid. If there was no liquid. No liquid. Okay. All right. So I'll stop here. I'll stop here. Hope you found the last one useful. Hope I didn't overwhelm you. It is a nice question, and yeah, because I really enjoy this part that the water resistance is proportional to speed. So this is give you another insight that you can use Newton's second law in slightly more sophisticated scenarios. Okay, then see you all next week. Enjoy.
Thank you.
You're welcome. See you.